Now let's take a look at an example so we can see how to use those generalized equations from our previous video. So here we want to find the transfer function, which is theta 2 over t for the system shown below. And so notice in this system we have an inertia, we have a couple springs, we have a couple viscous dampers, and then we have a couple fixed points indicated by these blocks with dashed lines in them. And so in this case we're given our theta 1 and our theta 2, but in some cases we might not be given all of that information. So if we wanted to figure out how many equations we need in general, of course we can say our number of equations is equal to our degrees of freedom. And so as we talked about a couple videos ago, for our rotational mechanical systems, we can say if we're holding all other points in the system still, can we still rotate this point? If so, that adds a degree of freedom. So for this system, we can say if we hold this inertia still here, then we can still rotate this point over here where theta 2 is. And vice versa, if we're holding theta 2, we can still rotate our inertia over on the left. So in that case, we could say that we have 2 degrees of freedom, and of course that means we need 2 equations. Okay, so let's go ahead and write those 2 equations. And so you notice I have numerical values next to all of our components in the system, as well as some green labels indicating, for instance, J for our inertia, K1 for one spring, K2 for the second spring. And that's just because I'm going to write a general equation first and then insert our numerical values just so we don't get mixed up, because you might notice that all of those values are 1, just to keep things simple at first. Okay, so we know we need 2 equations. So for our first equation, let's go back to our general equation and see what we need. So again, because we only have 2 degrees of freedom now, we're only going to need 2 equations. So basically we're not going to need anything beyond the first 2. Because we only have theta 1 and theta 2, anything on the left side beyond theta 2 we're not going to need either. So we're just going to have 2 terms on the left side of each equation. So in our first equation, we want sum of impedances connected to theta 1 multiplied by theta 1. So coming back down here, connected to theta 1, we see we have our inertia, we have our spring K1, and our viscous damper D1. So what we can do then is we can say for that first equation, we have our impedance of that inertia is Js squared plus D1 times S, so I'm just summing all of the impedances for those 3 components, plus K1, so that's the sum of the impedances. Now we multiply by theta 1 of S. Okay, so that's our first term. For our second term now, we want to subtract the sum of impedances between theta 1 and theta 2 and multiply that by theta 2. So coming back down here, between theta 1 and theta 2, we see we have just the spring and the viscous damper. So we're going to subtract the impedances D1 times S plus K1 multiplied by theta 2 of S. And then finally, looking at our generalized equation on the right side, we have sum of applied torques at theta 1. And in this case, we have our torque T being applied to theta 1. And again, that's being applied directly to theta 1, which is why we include it here, so T of S. Now, if I want to plug in values, of course, coming back up here to my figure, I can say for J we have a value of 1, for K1 we have a value of 1, and so on and so forth. So eventually what this is going to reduce to is just S squared plus S plus 1 times theta 1 of S minus S plus 1 times theta 2 of S equals T of S. Okay, so moving on to our second equation. So for our second equation, we're going to follow a similar procedure. So our first term is sum of impedances between theta 2 and theta 1 times theta 1. And again, we're subtracting that term. So let's go ahead and put that minus out front. And between theta 2 and theta 1, of course, that's the same thing we just looked at in our previous equation. So we have our spring K1 and our viscous damper D1. So we're going to sum those impedances, so D1S plus K1 multiplied by theta 1 of S. Now for our theta 2 term, we're adding, so coming back to our general equation, so we're adding sum of impedances connected to theta 2 times theta 2. So coming back here, we see, of course, we still have our spring and our viscous damper connected. Now we also have another viscous damper and another spring connected. So we have 4 items connected to theta 2. So we're going to have d1s plus k1 plus d2s plus k2. All of that multiplied by theta 2 of s. And then for our second equation on the right side, we have sum of applied torques at theta 2. And we notice that there are no torques applied directly to theta 2. So there are no torques being applied here. So we're going to set the right side of this equation to 0. Again, I can substitute the values. We know that d1, d2, k1, k2, all of those are equal to 1. So if I substitute those in, I have negative quantity of s plus 1 times theta 1 of s plus the quantity of 2s plus 2 times theta 2 of s equals to 0. So at this point we have 2 equations, 2 unknowns, because remember s is just a variable. So what we can do is we can use Cramer's rule to solve this because it's a relatively simple one. So we looked at Cramer's rule with our translational mechanical videos, so I'm not going to go into the process in as much detail, but essentially we're going to create a coefficient matrix and a constant matrix and sort of play around with those a little bit to solve for our theta 2. So we can get that our theta 2, so our coefficient matrix is s squared plus s plus 1 minus s plus 1 minus s plus 1, 2s plus 2, so determinant of that in the denominator. Now in the numerator, remember we're taking that coefficient matrix, but because we're looking for theta 2, we're going to substitute the second column with our constant matrix. So this becomes t of s and 0. So taking the determinants here, we see that it's a little simpler than even what we saw in the previous example for our translational system. We have this times 0, so that goes away, and we're left with our ts times this value here. So in our numerator, we just have t of s times s plus 1, and in our denominator, we have s squared plus s plus 1 times the quantity 2s plus 2 minus the quantity s plus 1 squared. Again, relatively simple, but maybe a little more algebra than some of us would like to do. So from there, what we can do is we can clean it up a little bit, and we can say, of course, our transfer function, g of s, is that value, theta 2, divided by t of s. And of course, all we're going to end up doing is canceling out this t of s in our numerator here. So doing that and sort of cleaning up, let me show a couple steps. So we'll have s plus 1, and we have 2s cubed plus 3s squared plus 2s plus 1, sort of just factoring that out a little bit. And then we can actually cancel out an s plus 1 if we factor out the denominator, so we get 1 over 2s squared plus s plus 1. So that would be our final answer for our transfer function. And again, like I've said a couple times before, in class or with some supplemental videos, we're going to come back and see how we can solve these equations a little bit easier using a program like MATLAB. But again, it's always good, in my opinion, to sort of know how to do them by hand if needed.